test. All right, so view full screen. Okay, so today we are moving to actually doing machine learning and using techniques in machine learning. In this case, it's neural networks. The idea is that we are going to start by talking about the classification problem. The classification problem is when we have a data set, which the predictions for this data set is a categorical prediction. So it's either true or false, or is noise or signal, or is 0, 1. The possible labels for our data only can take 2 values. This is a binary classification problem. For example, here I'm showing you a simple classification problem, often used as a benchmark for computer vision, which is the ability of distinguishing cats and dogs. And let's say you want to distinguish dogs. This is your signal. So when you see a picture of a dog, you want to say it is a dog, and you don't want to confuse it with another pet, which is a cat, and sometimes they look quite similar. Small dogs, some cats with different colors may look quite similar. Or maybe if we're getting closer to home, you are looking at events in the Large Hadron Collider, and example, in this case, you're looking at events with 4 leptons in the final state. And you would like to know whether an event with leptons with a particular momentum, this PT or the 4 lepton, could correspond to the standard model production of the Higgs, or to the production from other standard model processes like ZZ or so on. Okay, so you would like to classify these events as being standard model-like, or maybe events that could tell you that new physics is at play. In this case, the problem you are looking at is also a classification problem. For example, is this being an indication of new physics, or is an indication of just normal standard model processes? And of course, your answer is not going to be categorically yes or no. It's going to be mostly yes or mostly no, with some probability attached to it. Okay, so what we want to do is to take the inputs. In this case, for example, there are images of cute cats, or in this case, there are properties of events in the Large Hadron Collider. You would like to transform them, and then this should give your prediction for being standard model or BSM or new physics, being a cat, being a dog, right? And the labels, the output of this transformation, binary classification problem, can be set as a 0 or 1. Or if you want to think in terms of probabilities, you might give an output that is neither 0 nor 1, is a number between 0 and 1, with the higher the number towards 1, the more signal it is, or the number more towards 0, the more noise it is. Okay, so you might want to take your inputs, and as output, the transformation the model you want to propose might not give you a simply 0 or 1, it might give you something in between. That said, for example, what you could do, you could take your weights times your data and call this Z a new variable if you want. Make a transformation on this Z that could look like this function, which is called a perceptron, or this other function called a sigmoid. If you are on this side, you are mostly background. If your result is on this side, you are signal. Okay? But it's in the perceptron, this is a steep going up. So at 0, it changes from 0 to 1. So the answer for this heavy side theta is always going to be or 0 or 1, but nothing in between. But there are other outputs that you could decide to use other models for your data in which the output is 0 for small values, 1 for large values of this transformation, but somewhere in between you could have something closer to 0 or closer to 1, but not exactly 0 or 1. Okay? So, and this is maybe clearer when we think in terms of these events over here. Your x is going to be some number of events in a bin of energies for the 4 leptons. When you ask the question whether, for example, this bin or this data point or that data point or so on are signal or background, it's clearly the case that you are not going to be able to say it's signal or its background. You are going to give some probability for it being the case. So for you as a particle physicist, it's more sense to use a function, a transformation that goes smoothly from 0 to 1, but not necessarily makes a jump like this one, because you're not going to be completely sure. So notice that here, for binary classification problems, since the output is from 0 to 1, it has similar properties, and you can interpret it as a probability. We are already talking about probabilities. This is the way we naturally think about these kind of classification problems. So in binary classification, this is what is done. Remember that what we want to do is learn from data to classify very precisely. And for that, you need to learn based on some cost function, something that is telling you the criteria that you are using to improve your learning. So it's up to you how you write this cost function. A smart cost function will lead to rapid learning. A stupid cost function might lead to no learning or a very slow learning. So in the case of binary classification problems, the cost function that is used is related to the concept of probability. And that's something we can do in binary classification because precisely the outputs are 0, 1, and you might think on those as being a range, a continuous range between those two. So we interpret the output as a binomial probability where probability of being signal is going to be the output of this transformation. And since this is a probability and that is binary classification, then the probability of being background, so y equals 0, is then just 1 minus the probability of being signal. So think on this again in particle physics as when you have an event, whether it's bit act or not, whether it's new physics or not. You would like to know to a good accuracy whether what is your bit tagging. But this is never going to be 100% accuracy or 100% confidence. Might be very close, but it doesn't. It's not going to. So in logistic regression, which is the way we think on these binary problems, the idea of this transformation is then to assign some kind of probability to a data point as true or false, as signal or background, as bit tagged or not bit tagged. And following the logic of using probability thinking for the binary problem, we can define the cost function. And again, this is our criteria so that we choose as humans. This is our choice. So we do it in a way that makes sense from the physical point of view, is to use a cost function based on understanding from, for example, two-state energy systems in quantum mechanics and so on, that is called the maximum likelihood estimation, which is in rough terms, let's say, an expression that for a binomial probability problem tells us what is the probability that a set D is explained by a model W for a set of weights W. Okay, and the expression for this probability is given by this. Okay. Instead of using the probability itself, let me go back for a second, which is this probability over here, which by the way is very much something that you would use when you do Bayesian analysis, you might want to use a function that is a little bit better behaved. And the way to do that is to take this log likelihood, which is taking the log of that probability I just showed you. And that expression has two terms, right? It has a term that has to do with y. So for example, for y equals 0, 1, it corresponds to the signal, and then something that goes as 1 minus y. So you see, this way, the log likelihood shows very clearly that you have a kind of two terms, one giving you giving some weight and some understanding of events that go, or situations that towards probability 1, or no, sorry, towards being signal, and another that is weighting on things going towards background. Why do we do this? Simply because it has a clear analog in terms of what people have been doing already, like say Bayesian in probability analysis, and also because these kind of expressions, these kind of cost functions are better behaved numerically. So then if we have this log likelihood, and what we would like to do is to maximize the log likelihood, which is maximizing the probability that a data set is explained by a set of parameters, a model, a specific model, then the expression for these parameters that maximize this probability is again quite simple. You need to take this expression before and trying to find the maximum. Now, yesterday we were talking about the cost function with the idea that cost is bad, and what we want to do is to minimize it. Like we were talking about the error, the cost function being the mean square error, and we like to do is to minimize it, not to maximize it. So this is what the only thing we need to do in order to keep the same kind of discussion we had yesterday for linear regression, and what you did in your notebook is simply take a minus sign over here.
Veronica,
so
sorry. Yeah? So you said you have a theta there. I guess this is, I mean, you are maximizing with respect to the weight. What are you maximizing with respect to?
Yeah, so the idea is that this is the data point.
Yeah.
This omega, this is just because it comes from a discussion about Bayesian probability analysis. But essentially, this omega, we are going to, or you could characterize it with some kind of theta parameter that you are varying. Sorry, yeah, the notation is quite confusing here. This maybe forget about the theta. You are essentially going over all the possibilities of your weights. But in general, you're not going to just go over all possibilities. What you're going to do is parameterize your weights with some parameter that you are going to vary. And that will allow you to explore the parameter space of the weights. And that parameter that you are going to vary, we call it theta. And this is what we are going to maximize over. So we vary theta, which means we vary the weights, and we look for the maximum of the log likelihood. And that will lead to the best option for the weights. Is this a bit more clear?
Yeah, sure.
Sorry, I should have explained this. Good. So here the only thing we need to do to follow the same discussion as we did yesterday, remember we are trying to find minima in a complicated parameter space. And of course, it's the same as trying to find maxima in the same complicated parameter space. But since it's, the only thing we need to do then is to change the sign. And when we try to maximize the log likelihood, we are trying to minimize this cost function, which in this case is called the cost entropy. Okay, so for binary classification, the cost function is going to be called the cost entropy. Its expression is given here with a minus sign. And the interpretation or the kind of physical intuition that you gain from it comes, or if you are a particle physicist in particular, comes from having thought about, probability in the context maybe of Bayesian analysis. Okay, but it's simply a choice that you could have made other choices, and in fact, in some problems, this is not the best way to think about even the binary classification problem, but it's, let's say, it's commonplace, and this is what most people will use. Okay, changing your definition, your choice of cost function is just going to change improve it or maybe reduce it. In this case, this one works pretty well. And this is a function that depends on the data set and those weights, which again, we are going to be parameterizing in some way to be able to scan over them. And what we are going to find is that, yes, we will need to use regularization quite often, especially if it becomes a complicated and noisy data set. Okay, so logistic regression is following the same procedure we followed yesterday as in linear regression. We take a data set where now the outputs, yesterday your outputs were the number of rides that people were doing with their bikes, right? And the inputs were weather conditions, time, day, and so on. Here, the outputs are going to be binary. It will be either 0 or 1. We will build a cost function, which instead of being the criteria for learning, instead of being just the error, the difference between your prediction in number of rides and the reality, is going to be this cross-entropy function. We are going to minimize it, and with that, find the parameters that lead to the best prediction. And those parameters is what we call sometimes the model. We can, as before, as yesterday, we could use a regularization of the type L1 or L2. It's exactly the same procedure. So you can always add to your cost function, to your cross entropy, a term that is linear or quadratic with the weights. Binary problems, like the one I'm showing you, is an example of what is called categorical outputs. It could be that instead of trying to distinguish signal or background or cat dogs, you are actually trying to classify in terms of, let's say, colors, like you see over here, green, red, yellow, and blue. And then instead of having 2 categories, you will have 4 categories. As we were discussing yesterday with the issue of the seasons, assigning a value to each of these categories, 0, 1, 2, 3, you're assigning a value that is numerical, right? You're saying that, for example, green, it has a lower numerical value than blue. And this doesn't make sense, meaning that it might confuse your learning by bringing a variable that having no meaning by itself. It now has a numerical value that is a category, let's say, that is order. I could have decided to put in 0 blue and exchange it with green. The number itself doesn't have a meaning. To deal with this, often what we do is to use something that is called one-hot vectors. To describe the categories, instead of using this more, let's say, natural way in which you will say, okay, this is category green, I'm going to call it 0, category red, 1, 2, and 3, and just counting categories. What you do is to create vectors that have dimensionality of the number of categories, and for example, green occupies the first space, red the second space, and so on and so forth. This vectorization of your category label is very useful and speeds up things. It also democratizes the different categories, as it should, because again, the deciding to put here green instead of blue is just a convention. So it makes it explicit that blue is just a category which is exactly the same weight. It's just in a different position. Okay, so when we have more than 2 categories, all this discussion about using our intuition of probability can be used and generalized, and it gives to a new type of cost function that instead of being called the cross entropy is called the softmax regression, but it's very, very similar. Okay, so this is just to say that one can do classification problems with more than 2 categories, obviously, and there are a couple of things that you need to take into account. Now, let's say that we do this exercise, that we do a binary classification, taking a data set just to use something that we can think of, that all of us coming from different backgrounds can think of intuitively. Let's say that we are trying to measure the performance of our learning. And we would like to classify cats and dogs, where your main concern is, or not main concern, but you assign category signal to dogs and category noise cats. So how would you measure performance in this classification? Once you are done, you will say, well, my accuracy, how well I'm doing, will be to say, from all the cats and dogs I saw, how many did I classify correctly? Right? This is a measure of accuracy. And you could say, we now can distinguish cats and dogs with 95% accuracy, so you're super good at doing that. But maybe for you, because you've seen more of those, identifying cats is easier than dogs. In fact, you nearly always get cats right, 98% of the time. But sometimes you confuse a little dog for a cat. And maybe because you haven't seen that many dogs in your life, it's not that common to you. And it could be that in your learning, you might want to specialize in IDing dogs because you want to make sure you don't miss any. So for you, the fact that you are missing sometimes dogs because you are not used to those, and you are mostly being able to identify cats, is a problem. So I guess here what I want to tell you is that the question of classification and the accuracy of this classification is not like in linear regression, where you say, well, from all my data points, how far my prediction was from from reality, and I take an average of it, and I get a level of accuracy that kind of makes sense. You're treating everybody the same way. All these data points, you want to describe them overall in the same manner, as accurate as possible. But when it comes to a classification problem, you might want to treat the two classes democratically, and then a measure like accuracy is good. You just want to say, from everything, cats and dogs, how often was I good at identifying them? But more often than not, you actually care a little bit more about one category or the other. So things become a little bit more subtle. And there are other ways of identifying a measure of performance. So let's say that you want to focus on dogs. And I have a dog of dogs, don't get me wrong. I don't know, maybe because you were bitten by a dog or had a bad experience and you're really nervous about dogs. So your focus is on dogs. Like for a particle physicist doing experimental particle physics, you might want to focus on being able to identify the standard model very, very well, or this beta to a very high accuracy, and you don't care, or you don't care so much about other aspects of your analysis. So let's say you do that. You want to focus on dogs. You would like to be the best at identifying dogs because you perceive them as a danger. So what you will care about is, first, you would care about true positives. So from the dogs that are out there you might encounter, how many dogs you are able to ID. You also care about false negatives. So how many dogs you miss. Those are the ones that really worry you. Okay, but you also care about false positives. So how many cats are you confusing with dogs and they are making you jump? And also, finally, you care about true negatives. How many cats you were able to ID so they didn't worry you and you didn't have to, to think about them and just go along. So you see, there are different aspects of your classification that might be important to you, and you might also have a hierarchy of what is important over another. Also, in your learning or in the way you are trying to identify things, you might also have different thresholds. Let me give you an example. Imagine you are walking in the fields, and you are having a good time, maybe listening to music or something in your earphones, and you're really relaxed. In that case, your threshold for identifying dogs might be lower because you are not so stressed. Or imagine that you just had a bad experience with a dog on the way, then you become nervous, and then your threshold, you're trying to identify dogs with much more accuracy because you are really perceiving as a threat. So you look at this plot over here, which is called the ROC curve, and it's something that identifies the way you are learning or your machine is learning. It's a plot that shows the false positive rate and the true positive rate that you have in your learning. And and the machine as well, may be asking yourself or asking the machine different thresholds of your true positive and the false positive rate, depending on how alert you are or simply what kind of threshold you are actually asking to your machine. So for example, when you are over here, what you have is that your true positive rate is not too large, but also your false positive rate is also not too large. So you're not getting scared too often because a cat comes around, but you're also not identifying your dogs all the time. If you are over here, you are identifying absolutely all the dogs you see, but you are also making lots of mistakes, getting nervous and jumping because you see cats. Where would you like to be? Usually where you want to be is somewhere over here where you identify the maximum amount or a large amount of dogs and you don't get scared all the time with false positives. So you don't get overexcited because you see a cat too often. Okay. So this ROC curve, and you are going to see it everywhere, is like a measure of the ability that our algorithm has in learning and on performing. Where you place yourself along this curve will depend on your needs. For example, you are thinking on a new physics search where your background is gigantic, you might want to place yourself in a place where you are actually identifying enough signal, but you are not letting in too much background. So you want to be somewhere over here. But in a place where, or in an analysis where you have more or less a similar amount or expect a similar amount of similar background, you might want to be somewhere over here where you are rejecting enough background and keeping enough signal. Now, when you see ROC curves, often what the people do is to show different lines that correspond to different algorithms. And the idea is that the more this curve over here goes towards this corner, the better your learning is. In particular, there is a limitation, which is here. If you're learning, the output of your algorithm is over here, it means that you are making choices, you are identifying cats and dogs with a 50% score. Something like essentially you see something and you say 50% of the time is a dog and 50% of the time is a cat. So this line over here is no learning. It means it's just chance. So anything you do going in this direction, it means that you are learning something. Hence, there is another rough measure of learning, which is thinking about the area that is behind this curve. This is called the AUC. For example, an AUC near 50% will mean that from all this corner, you are just learning over here, so you are not learning because you are just doing chance. So anything above AUC, above 0.5, means that you are learning something, and the higher the value of AUC, the more that this curve is going to be in this direction. So it's going to be learning more and more. Okay, so the AUC is just one number instead of a curve and a set of points. It's a simple and very intuitive indication of your learning. Higher the AUC, the more you are learning. But again, sometimes, and depending on your problems, you might not care so much about the AUC value, but about other things. For example, you might care a lot about the precision, which is defined in our problem of how often when I say dog is really a dog. Or you might be
sorry, Veronica, what is AUC? What is the definition?
It stands as area under the curve. It's the
sorry,
area
okay.
under this curve. No, thank you for asking.
So the area, sorry, I'm confused. So the area under between the blue and the dotted?
No, the
everything.
area under everything. Over here.
But if you don't learn anything, there is an area as well. So
which is 0.5, yes.
Which is okay. So it's the difference with respect to 0.5. I imagine it's more or less. I mean, if you want to
yes,
measure how well you learn, it should be more or less the area between the blue and the dotted lines, no?
Yes, the definition of AUC is area under the curve, so it's the whole thing. And AUC 0.5 means your model sucks. Okay. And AUC 0.98 means you have a good model. And people keep it as the area under the curve and not respect to this line, because then you can also kind of talk about probabilities as well. 0.5 but has this meaning of a chance.
What I'm a bit confused is that, I mean, this is to measure. I don't know exactly. I mean, why is there a curve as opposed to just a point, right? You have made your machine learn, and then you measure some true positive, some false positive, and this is a point in this plot. So so the area is meant by what exactly? I mean, by
Let me explain this again because it's a confusing point maybe. When you learn, when you ask the machine to learn, the same as when you are giving predictions, you might be operating at different points. So as in this analogy of you are walking in the fields, your senses might be very heightened and you might be really alert, or sometimes you are really relaxed and you miss, for example, lots of dogs that are going around. The same happens for the machine learning. You don't have just one single set of values of true positives, false negatives, false positives, true negatives. You can ask your machine to learn with a given threshold. So you can ask your machine to be operating at one of these points over here. Okay, and this line what corresponds to is precisely the ability that your algorithm has to say that you want a false positive rate to be of this value. What is the true positive rate that it obtains? So the output of the learning is not a simple
but
set
what
of numbers.
I mean, what I would like to understand is what is actually that you are changing when you move along this curve, because I mean, it's not that you are. It's not a different algorithm, I assume. Otherwise, it doesn't have any meaning to say that this is the goodness of learning of a given algorithm, right? So what do you change when you move along this curve? Is it the data set you use to train? Is it the time you take to train? It is what exactly? I mean, I assume a given curve is associated with a given algorithm, but then what do you change in the learning process to move along the line, along the blue line? You know what I'm asking? In.
Yes, I know, because this is always a bit confusing. Okay, so what are you learning? What are you keeping here? You have exactly the same data set. You're not changing the data set. What you are changing is when you are learning. Well, so what you do is to run a procedure. In this case, is this logistic. For example, you do logistic regression. So your cost function that you are trying to minimize is this log likelihood type of cost function. And as you are learning, as you are going along and trying to get your best prediction for your model, you could be also be asking to your procedure of minimization of the cost function to compute at each point, for example, what is the true positive rate. And then when it gets to the best learning or to the minimum of the cost function for a given true positive rate. Saying that, for example, I say, I want to have a true positive rate of at least 0.5. So I'm setting myself in this point. The minimization procedure will go until it reaches that value, the true positive rate, and the minimum of the cost function. And that will give you a value also, the false positive rate. So this point over here, each of these points is actually computed running the same algorithm, in the sense that is logistic regression with the same data set, but with different threshold points. I can pass you.
I understand. Okay, thanks.
And yeah, thank you, Pilar, for asking, because this is really something that is shown a lot. Is like a measure of performance is very important, especially you will see in particle physics. And it's important also to understand. People that do, for example, B-tagging among you guys, probably this kind of plot, you cannot understand it, because if you remember in B-tagging, you have a working point. You choose your working point in which you are deciding what threshold of IDing B-tags you have, as compared with a threshold of not letting, for example, C quarks get into your prediction. Sorry, I didn't explain this very well. When you B-tag, you can B-tag very, very well. So every single, or not every single, but most of the B-jets you will be able to tag. But then you will also let into your distribution a lot of mistags. So, for example, from C-jets. So there are choices on how much pollution from C-jets you let in, and how many of the B-tags you are capturing. And those choices are precisely something similar to this RAW curve. I know that many of you are not working on B-tag, but since this is for particle physicists, you might be able to understand this. Okay, and for example, if you do medical physics, you might care a lot about some of these precision or recall or F1 score of other scores, because you might want to focus not so much on how many patients you ID correctly, but would you want to actually minimize the number of false positives, because for whatever, maybe your medical procedure is very invasive and you want to make sure healthy patients are not taking it. Okay. Hopefully, from all this discussion, you realize that there are lots of subtleties when it comes to classification problems. And those subtleties come because you have the ability to actually choose scenarios, to decide on focusing on one particular aspect of your classification. All right, any questions? I don't know how.
Sorry, Veronica, can I try to make some observation if I understood correctly this curve?
Sure.
So the idea that I got is that your algorithm at the end of the day is giving you a number between 0 and 1. So you put some cut. So if this number, say, is bigger than 0.5, then it is a dog. And changing this cut is giving you that curve, right? So you
Yes, that's right.
You don't train the machine every time. So that's the idea, if you, right?
Yeah, in practice is what you say, that you
Okay.
will simply assign a different probability threshold to a category or another category. But
Okay.
let's say the physical intuition, if you want, that goes over here, is the idea that you are essentially asking for a different criteria of what you call a dog or what you call a cat, which is equivalent to what you are saying. Thank you. No, that's a
Okay. Thanks.
good point. So yeah, you understood it better than me, actually. So that's good. Okay, shall we continue? So as you can see, there is lots of interesting aspects here, already a lot of intricacy in the binary classification. And for us, this binary classification, apart from being very interesting by itself, is also going to be a starting point from something, machine learning set of, if you want, architectures that is called neural networks. The idea of neural networks is that we are going to try to learn in a way that is inspired by biology, in a way that is inspired by what we think is the way our brain works, which is the idea that we have these neurons in our brain, and they have possible connections with other neurons through synapses. And these synapses are only established if there is enough electric current. So there is like a threshold for which a neuron will connect to another neuron, depending on some input and the value of this input. A high value of the input or the electric current will lead to a synapsis. A low value will lead to no synapsis. So you see, there is a sense of binary problem here, because it's either we connect or we don't connect. So neural networks are a framework to develop artificial intelligence. They're based on architecture made of neurons. A neuron is a building block for neural networks, and the idea is that a neuron is nothing but a transformation that you do on your inputs, leading to an output. So the idea is that the transformation that is called here sigma is going to be taking the inputs, multiplying them by weights and some biases, some shift if you want. That creates this linear transformation we call Z, which is made again of something linear with X. But then, and this is the important point, we take this linear function, Z, and then we apply on it a nonlinear transformation. This is exactly what we've done before when it came to binary classification. We took our inputs and we transformed them using, for example, a perceptron or a sigmoid in a way that is nonlinear, that it doesn't go linearly with the inputs. Okay, this, in the case of neural network, this output is given by an activation function. As in binary classification, this activation function could be a perceptron, a sigmoid, but now we can also have things that don't go necessarily from 0 to 1. They can go like a hyperbolic tangent from -1 to 1, or something that is called ReLU, which goes from 0 to something that grows with Z, leaky ReLU, or ELU. Okay, this is just different choices for this activation function. But it goes from taking very small values of Z, negatives, in this case, no synapses, to taking high values of Z and saying, yes, synapses. Okay, so neurons start with a linear transformation of the inputs to then perform a nonlinear transformation, which decides the output. This activation function doesn't have to be a probability like we were doing before. It can be something of this type. And sometimes precisely we want this kind of function because it performs better numerically. So the starting point for a neural network, the building block, is quite simple. It's something that is the basis anyway for binary classification. It's important that the first thing we do is a linear transformation, because Think about here you have inputs and their weights, and those are going to then be used as a whole, as a block for the activation function. So when you obtain the weights at the end of the day, you do your learning and so on, what is going to happen is that if you have a part of your input that has a small weight, this input is not going to be important because it's not going to be then transformed by this activation function. Whereas if you find out that in your learning there are some parts of your inputs that have large weights, that means this part of your input is important for the learning. So that linear part in your transformation is important for interpretation as well. Okay, so starting with this relatively simple building block, we can then build very complicated structures, these neural networks. This is called an architecture where you will input you have an input layer, you have an output layer that gives you the predictions, and in the middle you are going to have hidden layers which take the input, do transformations, then transform them again and pass them along to the other neurons, and so on and so forth. These are these neural networks where every layer, the neurons of every layer connect to every neuron of the next layer, are called fully connected neural networks. Okay. Each circle here is a neuron. The in arrows are transformed into output. So this information is processed by a neuron and produce an output, which then is the input for the next neuron.
Sorry, Veronica, one question.
Yeah.
So these connections between the layers are linear transformations or not necessarily?
Each transformation is the same. So the input,
right,
whatever it is going to be transformed with new weights and new bias. Okay. So everything that comes.
Yes, keep going. Maybe you answer the question.
No, it's correct. I understand. So here is clear, right? You take your X, you assign some weights and some bias, and you transform it. And the product of this transformation then is placed here. And
with
this new
weight.
neuron, exactly, with a new weight, exactly.
So it's you're making combinations in every step. You're making combinations of the output of the previous step.
Exactly, and with new weights.
I'm a bit confused. Sorry, also I'm a bit confused. So the so each of these circles refers to a weight. So in the first, let's suppose that we just have one line. Then this would correspond. I mean, if the output.
So each of these circles corresponds to this. This is the neuron. So what the circle will do here is take the output of this other one. Let me go back. Sorry, I hope you see the changes in the slides. It will take the output of the previous one, will assign some new weights, a new bias, and do this transformation on it. And
yeah, what I'm missing is the structure of the data. So you have X is a vector, right? All the inputs from the data, and then the set is still a vector that goes in the next line, or what is it?
Yeah, very good question. No, here X can be a vector, a tensor, whatever you want, and the weights are going to precisely produce a scalar out of this.
Okay, so set is a scalar at each.
Exactly, and as a scalar here is just a number over here. You apply this function, activation function, to this scalar. Okay.
Okay.
So the second thing you do inside the neuron is this non-linear function on a scalar.
Okay.
So whatever complicated X is, you need to change it into an array, a tensor, whatever you want. And then your weights are going to have a structure that precisely makes the whole thing being a scalar.
Okay, okay.
So each neuron has one wave per input and this offset.
Exactly.
Those are kind of the parameters that you will minimize when you perform your learning process.
Mm-hmm. And it's, as you can imagine, it starts from something relatively simple. Give me inputs, I give some weights and bias, and I just do this nonlinear transformation. It becomes an extremely complicated process. But since every step is clear and is exactly the same in the next step, it's just the inputs and weights that are changing, then there are lots of tricks, if you want, that one can use. So what this neural network is doing is transforming inputs that are here in the input layer, that's what you input to these neurons, and transforming them into a prediction, an output layer, at the output layer, by passing all these inputs into these hidden layers. If you want, what this is doing is taking the inputs and doing nonlinear transformations or many nonlinear transformations, right? So this is taking an input and doing a nonlinear transformation, which then is taken as an input for this one that is doing a nonlinear transformation. That is you get it. So by starting with something relatively simple, a neuron with a nonlinear element on it, you are actually, by building over it, you are able to represent the possibilities of taking an input and leaving to an output whose relations between these two could be extremely and highly nonlinear. Think that when we do this, we are just assigning, not assigning, but with weights that for the moment are just completely unknown. This is what we are going to search over, right? We are going to go over this, assigning some weights and seeing what minimizes the error, for example. But the kind of description you are being able to do, just changing values for these parameters W, are representations of relations between input and output that could be highly nonlinear. And as physicists, you probably realize that this is something that could be quite powerful. When we try to understand data, we often try to do it in a linear way or in some form of linear way. And if not, we modify the data in a way that this linearity becomes apparent. Simply because trying to do some function that is highly nonlinear and acquiring some intuition from it is hard. But this is precisely what neural networks are doing. It takes an input and an output and expresses many different possibilities that this functional dependence between these two could be, in a way that it couldn't be captured with some simple functional forms.
Excuse me, I have another question. Do you have to apply the function f in every hidden layer, in every hidden neuron, let's say, or only in the final output layer?
So let me make this very clear. Each of these guys, these circles, are neurons. They all do the same. Linear transformation and an activation function. You could decide that this layer will have an activation function of the type perceptron, and this one has ReLU or whatever, but they all do exactly the same. Linear times nonlinear. Okay, and you see that because this nonlinear, the activation function might be small, it might be that some of these outputs here are able to pass to the next neurons. On some of them, after transforming, will not be able to activate and go to the next. So information over here will not be passed. So also, the neural networks are able to, if you want to trim and get rid of information that is not useful. So after learning for some time, because the neural network what it does is goes around and around testing possibilities, it will start realizing that some parts of these inputs that then are passed on are really not that interesting. So it will stop activating some of the neurons. The weights will be small. So it's also able to start selecting and making a hierarchy of the importance of some of the features. Neural networks are then an excellent place to model complexity. Sometimes this is called, all this stuff I'm talking about, as how they have a high degree of expressivity or exhibit a high representational power. Simply saying that this neural network is able to express relations between inputs and outputs that could be extremely complex and that you will not be able to write down in combinations of many, many complicated functions. The more hidden layers, as you can imagine, as you extend this longer with more and more layers, and sometimes you have hundreds of these deep layers, the more complex the features or the relations you could represent. That's why in the context of neural networks is when we start talking about deep learning or deep neural networks, with the depth meaning the number of layers that you are putting in between, in the hidden layers. Okay, any questions?
Yes, I have a question.
Sure.
I would like to know the necessity of use of fully connected layers. Which is the difference with no fully connected layers?
You will see in the example today, it's very complete, and you will see that first we do a fully connected neural network, but when you build it, you can also decide to not connect everything. But I guess the idea is that in principle, what you are doing is exploring possibilities. So you will always start by building an architecture and letting everything go around. And in principle, you as a human don't have an intuition of which layers should disappear and which ones you should not. But when you build neural networks and you run over them, you can also have possibilities. For example, you might decide to do something called dropout, which is in a random fashion. From time to time, you want to drop some of these networks so that they are not fully connected. But in answering to your question, why using fully connected, what else would you use? I mean, how would you choose to connect and not connect some of them? You are precisely asking the network to find the information for you, information that you are not able to obtain because it's too complex. Okay. This lecture, sorry, is going to take a bit more, but we are really going to the core of what is a modern application, right, of supervised machine learning. It's the use of neural networks. Yeah.
Veronica, this plot looks very complicated. I assume in practice things usually don't, I mean, because the number of parameters is huge if you have weights for each of these neurons. So I can imagine the minimization problem to be completely, extremely complicated. So, I mean, are there rules about, like most of what is being done these days is using software that is done by someone else. So is this software, using some, to what extent can you modify this? And you should modify this. I guess you will explain this a bit more. But,
yes. So in the notebook, we'll see how we build these neural networks, how we modify them, how we vary parameters, the architecture, dropout, regularization, and so on. And yeah, so we will use things that have been already coded and with handles, if you want, that you can call for and you can decide to modify as well. Nobody in their right mind starts building a neural network from scratch. Because as you say, doing this minimization problem will be crazy. But yeah, you will say that this is extremely complicated, but it runs in a matter of 1 minute. I'll give you examples, and I think it will help. Yeah, I guess it's good that you guys realize that this seems extremely complicated, and it is. And the good news is that nowadays we can do this with the stroke of the keyboard. Okay. So now I'm telling you that I have, a neural network that in principle might be able to handle complicated features, relations that I will not be able to express linearly. Features, relations between input and output and normal functional forms, or let's say lines of code, or a function that I define in my code might not be able to express. And for that, I think computer vision and speech, human characteristics are a very good example. If machines are able to do some of the stuff we do in let's say, as we are born, then machines are in a good place. And I want you to, what we are going to do is to discuss a tiny bit one thing that we humans do all the time without even realizing. And I want you to realize how complicated it is. Okay, so coming back to the concept of cats and dogs. Here I'm showing you some pictures of cats and dogs. And I'd like you to look at them and think whether you have any doubts that what is on the left are cats and where the things on the right are dogs. Okay? And you see the dogs, of course, take many shapes. The cats take many shapes and colors and everything. You even have here a cat that is sleeping with a little girl, and you still know it's a cat. You have probably no doubt that this is a dog. You know that this is a cat. Now, can anybody tell me, if you had to explain to a machine how to identify cats and dogs, what kind of instructions would you give a machine? I'm going to ask people if you know what it is. Let's say, I'm going to ask a question, okay? Carmen Duomo? Carmen, ¿estás ahí?
Yes, can you hear me?
Yes, I hear you very well. So can you tell me, Carmen, sorry to pick on you, how would you tell a machine those are dogs and those are cats? Like what kind of characteristics you see that allow you to distinguish those two?
Maybe the cats, they have more stripes, or I don't know,
Like for example, this one doesn't, and
that's true. Maybe the shape of the ears.
mm-hmm. Yeah, they look a bit more pointy, although for example this one is pointy. This one is pointy.
Yeah, or the eyes.
The eyes, meaning they look a bit different. But again, this we don't see the eyes, and we still, you will say it's a cat, no?
Yeah, I don't know.
And neither do I. The idea is precisely that. Realize of how amazing you guys are. You do a classification problem with, I would say, mostly 100% accuracy, and you can't even explain how you do it. Because it's just a lot of subtle differences that, yes, I agree. For example, many cats have stripes and dogs don't, and although some do, but you are able to classify those with 100% accuracy. It's not like more likely or more often or whatever. No, 100% accuracy. You know those are cats and those are dogs. Okay. Sorry, Carmen, yeah, that's enough. Thank you. And I hope some of you
No
have
problem.
have been thinking about it. What would you tell a machine? What lines of code would you tell a machine to be able to classify those two? And it's not good enough to say sometimes they have stripes or sometimes the eyes look different, but the nose. But what Carmen is talking about is going in that direction already. It's telling you that it's not good enough to focus on features that are, let's say, common among cats and not so common among dogs. It needs to be more than that. And some of these features, also, you need to identify them in images where the cat sometimes is filling the whole picture. Sometimes the cat only shows a head or is with other objects or near, a cage or with a pillow, Think of how complicated this task must be for a computer. Who it's not like a person who's opened their eyes and takes years to learn how to do stuff. It's a computer that knows nothing. It doesn't know where is a mini image. It doesn't know what blue is. It doesn't know, this is a cage or a pillow. This is a girl. It doesn't know this. But you ask the computer to actually distinguish cats and dogs. Period. Okay? So a big step in machine learning, which was achieved thanks to neural networks, was precisely being able to do this task with an accuracy that is very, very close to 100%, and that is able to match human accuracy. The way we were able to achieve that was using a type of neural networks that is called convolutional neural networks. The idea of convolutional neural networks is that when it comes to images, so visual, computer vision, often the features we want to focus on are local, meaning, you see, for example, in this image, you want to focus on this part of the image. This for you is obvious that it's a cat, and this is the body of the cat. But for a computer, you first need to tell the computer to be able to segment, if you want, this part from the rest. Or if you want to be able to focus on this, let's say I focus on the body of the cat, and then I focus on the eyes and things that are locally connected with respect to other things that are on the background and that are not important. So apart from shape and color, we know a cat is a cat because other things, relations among their features, for example, as Carmen was saying, the position of the eyes, the ears with respect to the head center, and this has to be achieved independently over the image of the cat, where in the image the cat is. So when it comes to computer vision, symmetries such as locality and translational invariance must end up playing some role in the identification task. So there is a type of neural networks that precisely is designed and built to take into account those properties of images. So it makes transformations that preserve locality and translational invariance. Okay, so this is the typical plot you will put for convolutional neural networks. The idea is that is a set of layers where you start with an input given by, if it's a color image, the three channels of the color, so red, blue, and green, and an intensity in each of the pixels of this image. Then you do a transformation to a set of transformations to this image, and these transformations are something that is called pooling, and the other is convolution. What is pooling? Pooling is simply trying to simplify the image. Let me go back for a second. You see in this image there is, if I separate, let's say, between, I don't know, 244 pixels versus 244, there is a lot of information, but a lot of it is kind of continuous. We have this blanket here blue, or we also have the cat, the body being in precisely this position or a bit later on is not that important. So a simplification we can make to the image is to break it in pieces, in the areas if you want, and take, for example, break it each 4 pixels, take those 4, a matrix of 2 by 2, and substitute it by 1 pixel with the highest intensity of color. Yeah.
But in this case, Veronica, you would like to basically keep much more resolution in the head of the cat and much less in other features.
Yeah,
So
you might want to do that, but the pooling is not doing that. It's simply taking the image and pre-processing it first to make it a bit simpler. That's it. There is no, like, it's not smart in that way. You simply reduce the initial image to smaller number of bins, where you substitute the one with the highest intensity on it. And then the interesting part.
Does doing this you lose resolution?
Yes, you do. You do lose resolution.
And why do you choose the highest pixel value and not the mean, for example?
That's another choice. The pooling is based on or it's called max pooling, which takes the maximum, and there is another choice where you could take the average. So there is the reason that it works better, but there is like no underlying reason. So that's the max pooling. Will take the maximum, and you could do an average pooling, which would take the average. So most commonly you use max pooling. Okay, so the typical first transformation or a transformation you will do is simply reduce the resolution of your image so you can handle it better. But the smart transformation, it comes from the convolution. So what you do is you take the spatial information. If you think on this over here, imagine that there is an image. Forget about the colors for the moment, it's just an image. And you are trying to identify a cat. And as Pilar was saying, you probably care a lot about the eyes over here. But more than the eyes over here, you care about the fact that there are some objects here and the relative distance between these two. You have to be able to identify a cat, no matter if it's in this position or with the girl as before or in some other position. So what you care about is really about relative distances, about this, the fact that things are close or not to each other. So you care about locality, and you also care about relative distances among objects. This can be done in a transformation of your inputs and the distances at the beginning that is made to mostly retain information about relative distance, how far things are from each other. Okay, so maintaining is an operation, this convolution, which takes the inputs and tries to reduce the information inside this image while maintaining these spatial relations like locality and all the translation properties. Okay.
So how does this do? How is this done? I mean, it computes correlations of height, for example, between different points, and then keeps this correlation.
Yeah,
okay.
That's something along these lines. Yes.
Okay.
It's a mathematical transformation that takes the height, width, and depth for each of these RGB channels, and that's a convolution, which is what you say essentially. I didn't write the expression here, but it's something like this. Now, why do we do this? The first thing is that we need to to learn. And as again, coming back to your own experience, when you see a cat in an image, let's say, let's go back here, let's say over here, rather what will be a complicated task for a computer. You're asked, is there a cat in this picture? And you say yes, and you don't care. When answering this question, you completely don't care about what is around, right? Because just care about the cat. The problem is that in images, there is too much variability and too much noise and too much stuff that we don't care about when we want to ask a question. And that question is whether there is a cat or a dog. So it's too much superfluous information in an image. So the first thing we need to do is to transform the image and capture the essentials while maintaining the spatial relations. And that's why convolution and pooling is done. Now, you do this many, many times. It's not like you do it once and then try to learn something.
The first step is actually convolution and then coarse graining.
Yes.
And then, okay, that makes sense, I think. Because you want to avoid throwing away too much resolution when maybe it's very relevant. So
although it could be that your image is high res and you start with max pooling. So it depends. Doesn't have to be that order.
Okay.
Okay, so this passing through convolution layers and max pooling and so on, you are going to do it more than once. You are going to set, depending on how complicated your task is, you are going to do it through several layers where you start with an image with a clear human interpretation to, as you advance into the layers, if you try to understand what's going on or what is being transformed inside the hidden layers, you will not be able to understand. So it goes from an image with all this noise and superfluous details into something more and more abstract. Okay, so that's the main idea of convolutional neural networks. It's a smart way of dealing with systems where the relevant information is mostly captured by some symmetries or some local properties. Okay. Now, convolutional neural networks are extremely good in computer vision tasks, and there are other neural networks that are specialized on human speech, neural networks that are specialized on time series or time evolution of systems. There are neural networks for many tasks that are quite complicated and make them very good at learning. Why are they learning well? It's because neural networks are able to learn from data with little domain knowledge. And what I mean by that is that when you put images and tell the CNN to learn what is a cat and a dog, you don't need to give many instructions. You just say, this is my data set with cats and dogs. Become better at finding them. Next time I show you a cat, be 99.99% sure it's a cat. And that's all you say. Is you are not given specific instructions of do this or that. Of course, you set up your neural network that already has the symmetries you expect for your problem. So then this learning becomes easier. But even a simple, fully connected neural network is able to do the task of identifying cats and dogs. And this is what we are going to do later on. So it's not that you need to do these specialized neural networks, convolutional neural networks, to do a complex task. Actually, neural networks of a simple form, the fully connected, can also do this task very well. So neural networks can learn from data without much instruction. As long as you give, in the case of supervised neural networks, some labeled data, it's going to find by itself some way of learning about it. For example, I guess this is not so different from the case of humans. One of the properties that many physicists have is that because they work hard at problems and they learn how to learn, when a physicist changes area or goes somewhere else, they can also become quickly good at some new task without a lot of domain knowledge, without spending maybe years learning about the specific language and concepts in a new area, because they learn to learn. The same is for neural networks. They are good at learning. They are able, in the case of deep neural networks, to take large streams of data and learn features with very little guidance. And in that sense, they do work a little like black boxes, okay? But also think that in the sense that you give data and it gives you an extremely good prediction after learning, and you, in principle, have no clue of how it did it. Then you have to go back and dig and try to understand what kind of procedure it used to learn from data. But again, because these deep neural networks are actually establishing relations that are highly nonlinear and extremely complex, you might not be able to interpret it. So that's let's say, the downside of neural networks. They are good, but they are also difficult to interpret. Neural networks in particular are important nowadays because our problems, our complex problems, tend to be populated with lots and lots of data. The amount of data in each problem that society or any physics had to deal with is increasing, always increasing. And it is known that the performance of neural networks, especially deep neural networks, becomes stable with the amount of data, whereas other methods, for example, this logistic regression I told you about, it really suffers with the amount of data. All this minimization process that we need to do, if you just do it a la normal, let's say with logistic regression, and you try to do it with large amounts of data, it really suffers from it. Why is that? Why are the neural networks so efficient at handling lots of data? There are many reasons, but mostly it comes down to the fact that neural networks are made of simple things. They are made of, well, at the end of the day, it's a 0-1 gate. And you take these gates and you place them in layers, which allows them to be parallelized, to be very good for GPUs and so on. And then to scale better than on other learning models, like, for example, support vector machines. Okay, what we are going to do today is, this is what I'm putting here is a very long and complete notebook. I don't expect by 12:30 you will have done everything, but at least to go over it, because we are going to take a standard data set of images, and we are going to do a classification problem. Instead of being a binary classification, cats and dogs, we are going to do even more complicated. Not even more complicated, but even with more complexity, which is classifying handwritten digits. Again, this is a task that you as humans can do very well. For example, you see that all these are zeros, all these are ones, or twos, or threes, or sevens, for example. You realize that because you've seen many of those numbers before. In particular, for example, take this 7. Sometimes people write it with a bar over here. Sometimes they do like this. Or 5s. For example, I write 5s like this because I'm a lazy bum. But some people are more dedicated when writing their 5s. Handwritten symbols, numbers, have a lot of variety on it. But those, at the end of the day, are images. So maybe using convolutional neural networks, we might be able to achieve a good accuracy and identifying numbers so that the next time I show you a handwritten 0, you know with a probability close to 100% that this is 0. Okay? So we are going to build and train a neural network to become better at recognizing these handwritten numbers. This is going to be a supervised machine learning problem because we know the true labels, so you will have images. This is a database called MNIST, of handwritten numbers with their labels. So there will be an image, comma, this is a 0, image, comma, this is a 1, image, comma, this is a 2, and so on. And we will have about 100,000 examples of this. What we will do first is build a fully connected neural network for which you can play and run and do stuff. I'm going to show you in a second. And we will get an accuracy that of the order of 96%, meaning that when you learn from, let's say, 60,000 images of numbers, learn using just a regular neural network, and you test on thousands of other images with no label on it, you will realize that you have an accuracy of 96%. So it's pretty good. I mean, it's pretty good, but it's not like a human. We want an accuracy at the level of a human. And this will be achieved by using, instead of a fully connected neural network, a specialized neural network, a convolutional neural network. So with that, we will achieve 99%. And if we want more than 99%, we will use yet another trick, which is called data augmentation. The idea is that maybe 60,000 images are not good enough. We would like to have more, but we don't have more. So what do? We do something, a trick that is called data augmentation. The idea is that you take your data set, let's say that is done by 60,000 of these kind of things. And when it comes to the neural network, all body cares about is these relative distances, right? So what you can do is to enlarge artificially your data set by taking images like this 0 over here and applying random transformations. Like you might want to take this image and create a duplicate where you are rotating the 0 a tiny bit. Or take this image, a duplicate where you are making this contrast between the white and the black a bit smaller. Or you may take again this image and duplicate it, but now you zoom in or out, or you enlarge or reduce the relations here. This is called data augmentation. It's a way of making also your algorithm more robust because you show the algorithm in its learning more variability. And our precision then will go above 99%. Okay, so tomorrow we'll talk about unsupervised, but let's now go to the Google Notebook. I want to show you a few things. Can you see my notebook right now?
Yes.
Yes.
Perfect. Okay, so it's very similar to yesterday at the beginning. You can import the Google Drive. You don't have to actually for this particular notebook. It's not necessary. And what we are going to do is to build, this is completely started, neural networks using a package called Keras. Keras is essentially a package that contains very simple commands to build neural networks. Nowadays, Keras, which is the package we will use, is built inside another bigger package called TensorFlow. I told you that TensorFlow and PyTorch are two frameworks to do machine learning. So now TensorFlow also contains Keras. Okay. So we are going to use this data set, as I said. We are going to do some transformations as yesterday. What we are going to do is first we will load the data. Keras already has inside this data of MNIST so that we don't have to get a folder somewhere or a file somewhere and then put it up. And we can actually just call the data with this NIST load data. We are going to then separate our data between the training, validation, and test. The idea is that, for example, from all your data sets, you will take 80% for training, 10% for validation, and 10% for test. And you will see why we separate between validation and test. The idea is that validation will allow us, as we are training, to monitor the performance and maybe to stop the training and change the parameters before continuing. And only at the end, when we are finished with our training, by looking from time to validation, then we test on a completely new and never seen data set. Okay, so we will use some of the calls of sklearn, like yesterday, the train test split that we discussed. We will look at the data. Let me just go quickly over this because the point of the next hour now is precisely that you go over it. The first thing we are going to do is to transform this data, that is images, so let's say it's 28 times 28 pixels, into something that we can input into just a normal, regular neural network. So what we do is to take each of these bins and we kind of unzip them. So we take these different bins as an array of intensity or gray. I don't know if you can see my pointer. Take the next layer and then place it beside. Place the next layer, you place it beside, and then from this image, you kind of unzip it and make a very long array. And this array is going to be your input for a fully connected neural network. We do that, we use Keras. With Keras, you can call something that is called sequential, and what sequential allows you to do is to build layers of neural networks by simply calling different layers. For example, I take my model that is going to be a sequential deep neural network, and I say to my model, add a layer of dense, of simply neural networks. Then I add another layer, Okay. Then you are going to train your neural network, and it's going to be able, yeah.
Excuse me.
Yeah.
Does the word dense mean fully connected?
If it means you have one layer of neurons. Dense means because you have, for example, 32 neurons in it.
Okay. Thank you.
Very good. I'm not going to explain everything because part of the next time, the idea is that you guys go over it, but I want to give you just the highlights, okay? So sorry if I'm not going step by step. But essentially, after defining your architecture, building your neural network, you are going to fit it. So the idea is that you are going to take your trained data set and you are going to get better and better in each iteration of running through the neural network, coming back, running through the neural network, coming back, and so on. You are going to get better. And these are these epochs over here. We do 20 epochs, where we start with an accuracy of 0.9 already in the first batch. The first run over the neural network is good enough to get to 90%. And we end up with something of that, at least for the training set, it looks like 98% accuracy. But then this is on the data you've been looking at and getting better at identifying. When you actually check it on the test data set, this 10% that you have never seen, you get something of the order of 97%, which is normal. You get a lower accuracy. Okay, and typically what you are going to do is for each of these epochs, so you run through the neural network 20 times, and the idea is your loss function, your cost function has to go down. This is what happens in your training, but your validation tells you that it goes down at the beginning and then you go up a bit, meaning that you are not generalizing very well. Same for accuracy, you go from 0.9 to reach a high value, but when you show it to a new data that you have not been training on, it doesn't get that good, okay? Which is again normal. This neural network is kind of, it's not overfitting a lot, but it's kind of overfitting a bit because it's getting a 1% better result on the training than on the new data. Now you will say, okay, well, 97% is fantastic. What are we talking about? Well, it's not good enough. And you know why the fully connected neural networks are not doing that well, quote unquote? when we do convolutional neural networks, which is this max pooling convolutional 2D that you see over here, we are going to reach accuracies that are higher and more consistent also, see over here. They are 99% or something like this. Why is that? The reason is that convolutional neural networks are already set up to look at images and look at these relative distances. Whereas, let me go back, sorry if you're getting dizzy with all this going back and forth. When we train our fully connected neural network, the first thing we did was unzip this image and make it into a lone array. So what have we lost when we did this? When we modify and transform the image into a lone array? Voy a preguntar a alguien. Jesús Guerrero, what do you think? Jesús?
Yes, can you hear me?
Yes, I hear you very well.
Okay.
The question is...
maybe...
Yeah, go ahead.
Yeah. Maybe I lost the shape.
You lost the what?
The shape of the number. If
the
you
shape
have an
of the
array.
number. Yes, that's correct. That's what happened. So when you unzip this, that information of, let's say, this is just below these other things, the shape itself is not completely lost, but it's less apparent than when you do a convolutional neural network where you are actually keeping the image as it is and transforming the relative distances. So you see, a fully connected neural network, although you are giving it to the network something that is not optimal to understand the true properties of an image, is still getting 96% accuracy. But when you actually give the neural network a good input in the way it needs to look at it, meaning the best way it can look at it, which is keeping the relative distances apparent, then it reaches much higher, well, a higher accuracy. Okay, so that's the main lesson over here, which is if you have some problem.
One question.
Yeah.
Can I make a question? So, but in principle, the neural network, since you are giving as input these arrays of numbers, it still has all the information that is about this image. So if the neural network is like completely super intelligent, let's say, it can you exploit all the data in the best way. It shouldn't matter what you give as input, as long as it has all the data.
Think that when we unzip this, the information that, for example, this pixel is connected to this pixel or that pixel is not apparent. Okay.
The arrays have an order, so I mean,
yeah, but
for example,
for example, let's say that now I tilt this a bit, or I make it smaller or bigger. So I agree. The information is there, obviously, because it's the same thing but unzipped, but the local properties are lost. They are there, so you can recover them if you know that this is what you need to do. As we will do, we will recover the shape of the image. But at least from the point of view of the fully connected neural network, you're not giving it in a way that makes it easy for the neural network to achieve this task. But you are completely right that if you have a very deep neural network and enough images, it's going to achieve close to 100% accuracy, because it's going to realize that something along these lines is going on. But it will take a much longer time and a much bigger data set. Okay? Okay,
it's clear now.
So what I was saying is that the lesson to learn here is that yes, as I don't know who was that, but thank you for the comment. Neural networks, if they are deep enough and you have enough examples, are going to learn whatever is to be learned there. Specialized neural networks like convolutional neural networks will make this task faster and possible when you have a limited amount of data set. So when it comes to images or when it comes to whatever is your problem, finding and using a neural network that is specialized to your type of problem, images, speech, time series or whatever, will just make things faster and easier. Yeah.
In these cases, you were showing what is the architecture. I mean, you had just one layer. How many layers in each of the cases?
Yeah, this is what you're going to do. As soon as I disconnect, you will see what this sequential.
Okay.
It is here. For example, you build a neural network. You define a model that is called sequential in this case, meaning it's going to be layers. You define the first layer as being this, with the input shape of your images. You define a second layer, and you define a last layer that is going to give you the outputs. It's going to be either 0, 1, 2, 3, the numbers. So this architecture in this case, it only has 3 layers, the input, the output, and one single intermediate layer. So for example, for the person who asked this question about, well, if you give it more depth, it might be able to improve accuracy. Totally agree. Since we have 60,000 images, one of your tasks will be to precisely change the architecture. Here I'm doing a very simple architecture with one single hidden layer that is called a shallow neural network. You can add more layers and make it deep neural networks. Same here, coming to what you were saying, Pilar. So here, your CNN is going to be defined again as a sequential neural network. So it will have layers. The first layer will be a convolutional 2D. Then you add max pooling, another convolutional, another max pooling, and then the last one is simply the outputs, which is number 0, is number 1, is number 2, and this has this kind of structure. Okay, and so this architecture is slightly more complicated. You could add more.
When you say deep, this simply means more than one layer, or is there a definition of what a deep?
No, there is no hierarchy. For example, when I do things in particle physics, I use 1 or 2 hidden layers, and that I will call shallow. When you, for example, in medical applications, you would use, I don't know, maybe 100 hidden layers. That's deep.
100?
Yeah.
So what is is there a rule of, do you know, given a problem, how many layers you should be using? Is this related to the amount of data? Is it related to, I don't know, what is?
Related to, yeah, so there is not like a rule, but I can give you indications. One of them is that if you have many features, you probably, so many characteristics that you want to describe or understand, you probably need a layer with enough neurons, and then to process all this, you probably need some hidden layers. Not just one, but several hidden layers to actually transform all these different neuron inputs. So problems with many characteristics, you want something that is a bit deep. Problems where you have a reduced amount of data, if you use a shallow neural network, you might get better results than if you use a deep neural network. The reason is that the deeper the neural network, the more it might start trying to find things where there are none. As in the example yesterday of the polynomial that is linear versus the 10th polynomial, the same goes for neural networks. If you have a reduced amount of data with lots of noise, you better stick to simple models. In neural networks, it means shallow neural networks. Whereas if you have lots of data, even if it's noisy, you might want to get more out of deep neural networks. So that's the only things I will say. It's a test and trial kind of thing. You try it, you see whether your performance is reduced, meaning that when you learn with a shallow neural network, it generalizes well, whereas with a thin neural network, it's not generalizing well, and that gives you a criteria. That's what your task will be today. Apart from understanding all this, I advise you to change the neural network architecture, the training epochs, all these parameters of your architecture. As you were saying, Pilar, it's important to just not take anything, but start playing with all these parameters. Change the train and test the splitting, change the transformations, stuff like this. Oh, and once you have this notebook, you can use it to any kind of classification problem with images, because they're the same steps. Yeah, there was a question.
Yes. So the number of layers might be related to the overfitting appearing in the training.
Yes. So the idea is that if you think on deep versus shallow, so deep, many layers, shallow, very few layers or hidden layers, the equivalent is what we were discussing yesterday about the linear versus 10th order polynomial. The 10th order polynomial was doing well when it came to very precise data. But if you start having noisy data, the complicated model, the deep neural network, is going to start trying to explain features that are just noise. But like yesterday, you remember we still had noisy data, but when we went from 100 data points to 10,000 data points, even though we had extremely noisy data and you could not see anything, the more complicated model was able to give a good description, because at some point, as you increase the data set, all these patterns that the complex model is trying to see are real, become real. So here is the same. If you have a reduced data set, better stick to shallow neural networks. If you have a good data set, then you can start enlarging the neural networks. So it's a misconception. Sometimes people think that you take a neural network, you make it as deep as possible, and for sure it's going to find everything or that is to be found. And this is not the case. In fact, it's the opposite. If you start trying to just deepen in your neural network, you are going to reduce your performance.
Okay.
Okay. Well, it's already 10 to 12. We will reconvene at 12:30, and I don't expect you have done everything in this notebook, but at least we can talk about what you've done and your questions. And I expect that you will continue working on this during this week. What we learned today is a lot of information, all right? So don't feel like you have to understand everything from the first try, okay? So let's then reconvene in 40 minutes, essentially. See you later.